So we're extremely happy to have Yi back for a visit. He's around for the week, and he'll be telling us about kinematic flow.
Thanks. Okay, so I start the talk by telling you the end. So hopefully you remain coupled, or you can decouple immediately. So I want to describe a toy model of that's supposed to emulate some features of primordial density perturbations and study them at recoupling at tree level. And I'll try to convince you that the right way to study, you get correlation functions that have some complicated analytic structure, and the best way to understand them is using differential equations, okay? Differential equations that depend on the kinematic data. They're anchored on the surface of initial conditions for the universe. And they have a life of their own, meaning I can predict the differential equations without looking at the standard time evolution of the perturbations. So that's the goal. But I want to start by framing the problem in a bigger context of understanding the initial conditions for the universe. So I want to review a little bit of what we know and what the near future has for us in terms of actual observations and what we hope to learn from data. So if you know this story, you should think of it as going to the greatest hits concert of your favorite rock band. So it's nice to hear what you already know. But hopefully after the beginning, I'll get to something new. And if you haven't heard, it will be a way to set up the context, okay? So the main motivation for studying these fluctuations are the initial conditions of the universe. Motivation is to understand initial conditions of Big Bang cosmology. And the way we learn about our universe is by studying correlations in the sky. So let me just make a little diagram. So here we are, we observe all sorts of structure around us at very large scale. We observe galaxies. They're my galaxies. We know that they are sitting in some scaffolding of dark matter. There's some cosmic web of dark matter and so on. And then we have some summary statistics of the distribution of this stuff.
You have to make the US look isolated from the rest of the universe.
I don't know we're in the US. I meant us. I meant us. Yeah. Let me do it like this. Better. Okay. Okay, so then we study some summary statistics. So for example, you can study the functional wave number, the deviation from the average in the density of the universe, the functional wave number, and you get this interesting curve. It goes up, goes down, has wiggles and whatnot. So it has an interesting structure. That's how we learn about dark matter, dark energy. You can repeat this type of exercise. There is a whole region that we haven't really observed directly that maybe one day with 21 centimeter radiation we'll be able to observe. This is still a big question mark. And then if you run the clock backwards, then there will be a point in which you should see the CMB. This comes from large-scale structure of the universe. And let me just hype you up for actually, so it was supposed to fly last week, but because of SpaceX, it hasn't been delivered yet. There's this satellite experiment called SphereX that is supposed to fly like now, that is going to hunt for a three-point function of density perturbations, particular type of three-point function. If you are familiar to the business, something that people call FNL local. Specific type of three-point correlation function that couples long wavelength perturbations with short wavelength perturbations. And we have bounds on this right now. And sphere X is supposed to either see something or improve the bounds, but well, depends on who you ask, but optimistically a factor of 10 from the current bounds. So that's exciting, the immediate future. And okay, so then if you keep running the clock backwards, you can also look at the temperature perturbations in the CMB. Now it's a snapshot on the celestial sphere, so we go to multipoles. We can plot this temperature 2-point function, and we see this beautiful acoustic peaks and so on, some damping tail or whatnot. And we know that in order to explain all this data, we need, at the hot Big Bang, at the surface in which you set the initial conditions for the evolution of the universe, we need some very special initial conditions. If you go back to wave number, it's convenience to write it in this form, the 2-point function of the density per the curvature fluctuation. This is the local curvature. You see that you need little inhomogeneities here. They're correlated in an almost scale invariant way. So this curve has some little tilt of a percent level, and it has an amplitude of order 10 to the minus 10. Okay, so these are 2 of the 6 numbers that you need to explain the universe. They have some amplitude and they have some scale dependence that for historical reasons we write as a number close to 1 minus 1. So these are 2 numbers that you need for from the CDM. You pick some pivot scale to normalize this 2-point function. And you write the power law like this. So these 2 numbers have been measured, and this is really all we know at the moment about the initial conditions in terms of measurement. Everything else we have bounds on the 2-point function of gravitational waves at the beginning of the universe, and also higher point correlation functions. And of course, this picture looks acausal, and we have a good paradigm for explaining where these primordial perturbations come from. So if there's correlation over long distances, we think that they were set up in some earlier periods by essentially sort of vacuum fluctuations that got stretched by the expansion of the universe, and we embed this diagram into some earlier phase of what we call inflation. So that's our current best bet for what the early universe was like. But from the 2-point function, we know very little about this period. We only know that compared to the typical energy scale during inflation, the Hubble scale during inflation, that this is a very light scalar field. We don't really know much more. And we would like to know what this theory is all about, where do these scalar perturbations come from, and so on. Moreover, there is this exciting possibility that if we do measure gravitational waves, which is something that people are actually trying to measure, so there's also 2-point function of gravitational waves, and if we measure them in the near future, there's another experiment that is designed to hunt for these gravitational waves. It's being designed with speed of light bird, spearheaded from Japan, that wants to put a bound on the size of the 2-point function of gravitational waves in units of the 2-point function of the scalar fluctuations. We know that they are percent level of this 2-point function at the moment, and this is going to improve this bound by an order of magnitude at least, maybe a little bit more even, or see something, hopefully. And of course, if you see something, it's a fairly robust prediction of inflation that you measure the Hubble rate during inflation in Planck units, which if we do see something, implies that this energy scale is very high. So it invites you to dream of the possibility of doing particle physics at extremely high energies, but that the universe gives you this very high energy experiment that is run just once, but at very high energy density. Okay. So the question is, so first thing, let me just, that part is becoming too busy. So R, the definition the ratio of the 2-point functions of the gravitational waves in units of the scalar perturbations. We know that it's less than order 10 to the minus 2 at the moment. And maybe we'll improve next decade by less than order 10 to the minus 3, maybe even more. But if R is detected, then the energy scale of inflation is very high, maybe something like this, 10 to the 13 GeV, which is very exciting. Could you imagine doing particle physics at these insanely high energy scales? So the obvious questions are, how do you do particle physics? So questions. How to do particle physics using inflation. And the other obvious question is, what is the field or field content responsible for inflation? And the tool that we have to answer this, we should use correlation functions beyond 2 points, or cosmological correlators. So, for example, the 3-point function of density perturbations, the 4-point function, things that involve the tensors, for example, etc. So there's a whole phenomenology of what kind of physics you can read off from measuring these correlation functions, the 3, 4, or mixed correlation functions, how do you do particle spectroscopy, and so on. And all of the physics is encoded in, of course, the overall size of these objects. It tells you about scales, but now that you go beyond 2 points, there's also some interesting shape dependence. So these things form some polygons. So I have here, triangle, ladder, and so on. And the question is, how does the signal go up and down as you dial the various geometrical knobs that you have in this correlation function? Okay, so that's. And so the first thing that if you want to understand these cosmological correlators, the first thing you need to learn is how to compute them. Okay. And so the main observable of interest are these 3 and 4 point correlation functions. But so how do you compute them? So the standard answer is from something called the Inin formalism, which is just standard time evolution from the vacuum state. Okay, so this turns out to be a bit too complicated. You for example, if you want to study the simplest thing, so for the rest of the talk, I'm going to forget about this, and I'm just going to think about how to do computations in this part. So here time goes up. So I just described this 2-point function of density perturbations, and you could imagine starting computing a 3-point function that comes from a self-interaction of this curvature of perturbation, or 4-point function, something a little bit more sophisticated. something that comes from the exchange of a new state. Okay, so how do you read off the physics of what's going on, the mass of these states, the spin, the coupling, and so on from these 4-point correlation? So that's the question. And there's a standard way, which is using, you have some sort of Feynman rules that you introduce for doing this computation in perturbation theory, and then you end up with some time integrals, okay? And even a recoupling, even with this very simple three-level exchange correlator, this is sort of a complicated problem, okay? Let me, by the way, let me just make a little parenthesis here that the searches for these types of cosmological correlators, they're template driven. So if you, so one thing that I think people should, for example, investigate that would be interesting, and maybe we could even try to put bounds today, not in 10 years, not to, like today, is if you have a new template that comes from other type of physics, it could lead to a shape function, a 4-point correlation function that has properties that people haven't searched for because they don't know what to look for. So let me give you an example. So let's say that these curvature fluctuations are going to blow up.
Sorry.
Okay. So say that these curvature perturbations are coupled to some operator of some strongly coupled sector, and then this strongly coupled sector has some interesting 2-point function. Some hole here. Then you have an exchange diagram of this type. I don't think the possibilities have been mapped out of what kind of features you would expect. Say you have like some QCD-like theory with lots of states around the Hubble scale during inflation, and you do this coupling. What sort of signature you would expect? There would be some interesting interference between many states. You won't be able to capture the templates just from this simple tree-level like exchange. So if you have a well-motivated template for what the correlation function would be in your favorite scenario for the physics of inflation, then you could try to constrain it right now, okay?
How much better are bounds with a precise template rather than sort of blind searches?
So if you, I know that the searches have been made for essentially this type of three-level exchange, okay, and as a function of the mass of the particle, but mostly for scalar exchange, and then it's more or less it interpolates nicely with what you expect. So there are two extrema. There's this extreme, and there's the extreme where the exchange particle is massless. So the bounds are much stronger for these templates when the exchange particle is massless. So it's better than more or less an order of magnitude compared to this bound. Now, if you put generic mass here, I think it's or it slowly interpolates. You get something in between these bounds. So just to give you some ballpark, this is FNL. The bound is of order 5. Here, oops, sorry, order 50. And here it's FNL, order 5. Now, I don't know if you start scanning from 0 up to certain value, whether these bounds get very, very slowly changing from here to here. I'm not sure. But for example, I think if you put the spinning particle here, there are no bounds at the moment. So they're just starting. I know the Cambridge group, for example, just started to think about what happens if I put a massive particle with spin here. Because if you add a spinning particle, then what happens is that the signal gets modulated, even if you keep the geometry more or less fixed, and you just start to change the relative positions of these 2 points with respect to these two, then the signal goes up and down. You have some oscillatory features that depend on the spin of the messenger. And as far as I know, this search hasn't been conducted thoroughly. Okay.
Because you mentioned it twice already, what is FNL?
Yeah, sorry. So FNL is well, you would think that the good definition of FNL is the ratio of the 3-point function to the 2-point function to the appropriate power, but that's not the definition in the literature. The definition in the literature is this up to some order 1 number is for example, the 3-point function divided by the 2-point function squared. Okay, which is a bad definition because even the FNL order 50 here means that the 3-point function is very small. You're just measuring it in the wrong units because you're paying an extra factor of zeta. It should be 3/2, but for historical reasons, we use this parametrization. So I forgot to mention that AS is ordered 10 to the minus 10, which means that you should think of each zeta order 10 to the minus 5, okay, the typical size of a fluctuation. So here you're paying an extra price of 10 to the 5. So even big FNL means that it's very, very Gaussian. So that's the definition. But it's just some proxy for the size of the correlation function measured in some units of the 2-point function.
Everything in these pictures are 3-point functions, right? Where you put one of the legs on the inflationary background? Are there genuine 4-point functions?
So the searches are done for 3-point functions, but well, so if you take this 4-point function and put one leg on the background, then you'll never be able to crank up this FNL so that it's actually measurable. Then what you do is you build templates in which you break the Sitter symmetries rather strongly by giving the input on a small speed of sound. And then you can do the searches. The templates don't get modified dramatically, but they do get modified, but we computed them. And yeah, so this FNL, strictly speaking, is for 3-point functions. But let me explain Nima's remark for the non-connoisseur. So one way to think about the 3-point function during inflation is to think of a 4-point function in the Sitter space and make one of the legs very soft. So for example, let's take this leg here. Make it very soft. So when you make it very soft, it essentially becomes a very slowly time-dependent background on top of which the other 3 perturbations experience the Sitter plus very slowly red-shifting extra wave. So it looks like inflation, slow roll inflation. And for example, Juan, now many years ago, computed this diagram when you exchange the graviton. Okay, and so if you do this exercise here, you put this, you do the graviton 4-point diagram and put one of the legs on the background, you reproduce his answer. So in which in the end, because it's the graviton, you're only really, it's not really a long range force. You just exchanging the Newtonian potential between the 3 perturbations, okay? This will be very small because inflation wants to, when there's an interaction vertex, he wants to make all the objects that come out of here have the same physical wavelength. But here you're creating a tension because you want this guy to have very long wavelength on top of which the other perturbations have shorter wavelengths, but these guys should have the same wavelength. So you pay a price for playing this soft limit. So you suppress the overall size of the signal. So you tend to get FNL much smaller than the values that we can currently bound. Okay, so you'll get, this procedure will typically give you FNL order ns-1, which is ordered 10 to the -2. So it's still 3 orders of magnitude away from what we can measure. So it's very useful. We can use a lot of symmetry, de Sitter symmetry, to constrain this, to compute this shape of non-Gaussianity. But if you want to see it to be around the corner, this is not the right way to go. But it's very useful as a stepping stone to get something more realistic. Okay. So there's a standard way to do this to compute these diagrams, which is by standard time evolution. Okay, you can introduce interaction vertices, time evolve them. Unfortunately, the propagators are very complicated, even for a massive particle in the Sitter space. These are some Hankel functions, the propagator, some hypergeometric function that you then need to integrate over time against these boundary propagators and whatnot. So you get something that is not very useful in practice. And turns out that the best way to compute this is to find some differential equation. So the working horse for the past 7 years or so to make progress in this problem, the working horse are boundary differential equations. So differential equations that only depend on the momenta on this surface of the initial conditions. So let me give you the example of the 4-point function with massive exchange. So here, if you are in, I'm going to do the computation in the Sitter space, and then I'm going to introduce the toy model later. But if you are in the Sitter space and you have curvature perturbations that you really want to connect to the data, you would like these particles to be very light, even massless. But there is a neat group theory trick that if you use conformally coupled scalars, which are conformal dimension 1 and 2, for the growing decaying mode, you can, if you get the answer for this correlator, you can just sprinkle it with some derivatives and whatnot to get the physical answer, the answer for the massless particle. So this is a very good stepping stone. So now say you want to study this correlator here. These are the external masses. Then you exchange a massive particle, generic mass. Then, well, long story short, there's a very nice differential equation that this object satisfies. Let me write the equation, then I introduce some notation. So let me explain what this stuff is all about.
That's only for this value of little n.
Say again?
Only for this value.
Yes, yeah, that's right. Yeah, it's important that actually I don't know. I think you can write some formal expression when all the masses are generic, but I don't have a reliable way of computing it for any kinematics with controllable errors and so on. So this is the case that at least I understand the best. So the reason why these masses are useful is because then these propagators are very simple. They just, this is time. So the usual, the Sitter metric. Right, like this is the metric. And here the propagator is very simple. Some wave number K. Otherwise, you have to put Bessel functions everywhere, and it's too complicated. We don't, at least I don't know how to do it. So, so let me just explain the notation. So first of all, when I remove an arrow from a vector, I just mean its absolute value. U is some sort of collective coordinate that is related to all the momenta that enter the left vertex. So U is defined by this. The absolute value of the exchange momentum divided by the sum of the absolute values of the momenta themselves.
Sorry, is this physically reasonable to only consider this mass? Or
So from this mass, you can find you can take this as some sort of skeleton from which if you sprinkle enough derivatives on it, you get the massless external legs, which is the case that we care for cosmology, because here you want these fluctuations to survive to the end of inflation, and if they're massive, they get redshifted away. So you want, okay, maybe strictly speaking, not zero mass, but you want them to be very, very light mass, and the massless regime is a very good approximation of the true answer. So ideally, you would like to compute this diagram for zero external masses, but this is a much simpler guy to compute first.
and this is very small enough to as a good approximation to masslessness.
It's not a matter of small, it's that the momentum dependence of the answer. So this is strictly speaking zero if you go to late times, but as is usual in say in ADS CFT, so you have this correlator, okay? So phi K1 eta phi K4 eta. As eta goes to zero, strictly speaking, it's going to zero, but then it goes to zero as eta to the fourth, and then you look at the leftover dependence. So, and this is the object I'm interested in. And then these objects, if I sprinkle it with enough derivatives and whatnot, there's something called weight shifting operators. Is related to the fact that they are related, they have the same kinematic constraints of a CFT 4-point function. Then you can get the actual answer for massless particles. Okay.
You can shift by integers in general, so you can shift not by integers.
Yeah, so that's why I chose 1 and 2 there. Right. So this is the variable U, and this is the mass of the exchange part. So what is the meaning of this formula here? So V is related to the energies that now enter this. You see that I chose badly the color. Let's see. That's okay. No? V is the exchange energy divided by K3 plus K4. Okay. So what is the physics story that we tell about this equation? Is that if you shake and bake these two legs in the right way, you sort of engineer the Klein-Gordon operator here, then you collapse this propagator, and this simple rational function is related to this contact diagram. Okay, so that's what this differential equation does for you. And then this delta U is some hypergeometric operator, it's a second order operator. This form. So then you can go and use 19th century, 18th century mathematics to solve these using theory of differential equations. Okay, there will be an equivalent equation delta V. We have a pair of all these, and then you can solve for this function f. If you ask me what are the boundary conditions, because it's a second order differential equation, then one boundary condition tells you that if the momenta become collinear, nothing special should happen, while the differential equation generically predicts that the solution will be singular there. So, for example, U going to 1, if you look at the definition of U, just means that the momenta 1 and 2 become collinear. And nothing should happen here, okay? So this is demanding that the solution is move around this kinematics is one boundary condition. And the other boundary condition, you go outside of the physical sheet, you send the sum of these energies to 0. So if I send the sum of these, so which is U, if you see, if take U minus 1, it's sending this guy plus this guy plus this guy to zero, which of course you can't do it for physical kinematics, you're just summing three positive numbers. But because these have square roots, you can do the second sheet and take the limits when the sum of the energy of these energies goes to zero. And what happens is that this is the best you can do in cosmology that is analogous to what we call factorization in scattering amplitudes. Scattering amplitudes, you can tune the energy to put a resonance on the mass shell, and the diagram factorizes. For the cosmological correlator, what you can do is you can analytically continue on the energies and send the sum of the absolute values of momenta, sort of the energies that enter the vertex, go to zero. And when that happens, the time integral that you'd have to do to evolve this vertex up and down, it's peaked at very early times. So you kind of drag this vertex backwards in time, and you factorize the resulting diagram. Okay. So these are the boundary conditions that then allow you to fully solve the differential equation. So this is an old story by now, but I just wanted to.
So you don't require anything to happen at the past? You don't ask for your things to vanish deep in the past?
No. You want the, there is a boundary condition that is related to demanding that all fields start their life in the vacuum. And the way it's implemented at the level of the differential equation is by demanding that there's no collinear-like singularity. If you inject some particles in the past, then there is a way, if you look at the diagrams, to see that there will be a singularity in these limits. But yeah. So while these other limits demands that this factorizes, you just drag this vertex to the past and you separate. You give this as many Hubble volumes as possible. Okay. So this is very useful, very powerful. Then you can do all sorts of things. You can spin up the external legs and you can the scalar perturbations. The differential equations are still there. And so then we were wondering quite a few years ago with Nima, our friends, where these differential equations come from. And here comes the toy model. So the question was, is this an accident of putting in a lot of symmetry? And the answer might still be yes, but we're going to try to cook up a toy model of cosmology that doesn't have all the de Sitter isometries and see if there are still these differential equations that only depend on boundary length. Okay, so question: are the differential equations generic in cosmology? And I think the answer is still we don't know, but well, maybe that's the answer.
Generic means for all masses?
Yeah. For all masses and maybe for backgrounds that are not close enough to the Sitter. So, and yeah.
In this case, just kind of conformal symmetry or?
It was useful, but it's not just conformal symmetry. So this is the fact that we haven't been able to fully diagonalize the conformal group. So this delta U operator is the operator that is related to the last isometry that we didn't diagonalize. So it is connected to it, but
I think this operator is the same as the Casimir. So there is particle 1 and 2, the two on the left.
yes.
You act with the conformal Casimirs and those two particles, and then because you know they combine two particles of mass m, you know what the value of that Casimir is, and that's the differential equation.
You mean this guy on the left, right?
Yeah.
Right. Now the fact, yeah. So that's definitely determined by group theory. But now there's some dynamical assumption that goes into what you put here on the right-hand side, and this is related to the fact that you then. I mean, this is what one should think of this as the Mandelstam at a flat space in the S channel. This equation is the precise analog. I think it's a useful analogy of if I take massive exchange scattering amplitudes, this is the scattering amplitude, S minus m squared. Right? This is the scattering amplitude. And you can rewrite it as S minus M squared times the scattering amplitude equals G squared, which is some operator acting on this guy, gives you just the pi to the 4. So this is what this equation is. Then there's some detail of why -2 appears here and so on. That's the idea. But then, well, so when we first discovered this, I explained this, then people were like, oh, but you put a lot of symmetry. But then you can start adding bells and whistles. You can make this inflaton have a dispersion relation. You can change the background a little bit, and the differential equations were still there. So then we were wondering if it was possible to explain them in a broader class of models. And so maybe, I think is the answer. So I'll explain a toy model for you that probably still has quite a bit of symmetry, but then we'll be able to move away from pure de Sitter or near de Sitter space and still find lots of interesting structures. And we'll go much farther, actually. Yeah. So let me. Our model is just a single scalar field, but self-interaction. So, and now I'm going to cheat by tuning the mass to the curvature of space-time, so it's conformally coupled, which makes the propagator always very simple. I still use this crutch that the propagator is sort of like a plane wave. Now I add some polynomial self-interactions. Okay, and but then I'm going to allow the cosmology to be power law. Eta over eta naught. And we were originally interested in near de Sitter. So this is the parametrization we used, and I'll show you a way of writing the correlator that makes this a natural parametrization. But you see, you can make this power generic, and lots of interesting cosmologies are captured by changing this parameter. So just this curiosity, like 0 is de Sitter space, then okay, -1, just go back to flat space. Then if you study -2, you get a contracting radiation dominated universe, -3 some matter dominated universe, and so on. So it's not lambda CDM, but it captures a variety of different cosmologies. And then well, we would like to understand how to compute the correlators in this theory, the endpoint functions. So first thing you can do is you can sort of canonically normalize and get rid of this mass term here at the cost of making these coupling constants time dependent. So let me just do that. So then if you redefine phi, then the propagator is as the simple form. I'm going to write the bulk-to-bulk propagator. Simple form. Theta plus into that plus and then there's a third term that you need to impose the boundary condition at the propagator. So this is the bulk-to-bulk propagator. So this is the standard thing that you learn in QFT 101, and then there's this extra term that ensures that the propagator vanishes, if I think theta prime. It ensures that the propagator vanishes when I approach this theta equals 0 surface, the surface in which I'm putting my fields on. And then I can sprinkle as many legs as I want because there's polynomial self-interaction and so on.
In the wave function.
Huh?
Expectation, but
This is for the wave function, yeah. Yeah, this is for the wave function. I mean, the differential equations are satisfied by the expectation value on the wave function, but strictly speaking, this is the propagator for the wave function. So just a side remark. So what Juan is saying is that I was talking about the expectation values of fields evaluated at the surface, but you could do a simpler computation first, which is what is the wave function, what is the probability that the universe in the vacuum state ends up with a certain field configuration at late times that is prescribed by a bunch of partial waves. And then you use Born's rule to get the expectation value, okay? So there's a wave function that depends on the value of the fields on this surface at equal to 0. And then from this wave function, you can compute the expectation values. We've been telling you about by the standard Born, be phi, psi squared, phi to the n. So this is the propagator to evaluate this wave function. So now you can write the formula for the time integral and whatnot. And but there's a neat trick you can do for this model that told us the way forward. And then we spent 3 years working it out. And then last year we realized that if we go back to this physics 101 way of parametrizing it, there's a much simpler way of seeing everything we saw in the past 3 years. But this is probably big news to Nima also. But let me explain what we first did. So let me start with the simplest example. If I do just phi cubed, okay, phi cubed theory, then this 4-point function will be given by the following formula. So K1, K2, K3, K4, and let me call this exchange momentum Y. I know I changed notation, but it's just the way it's wired in my brain. So K1 plus K2, I'm going to call X1. K3 plus K4, I'm going to call X2. So X1 is related to these energies that come from the left part of the diagram, and X2 from the energies that come from the right part of the diagram. And the wave function in this FRW, in this power law space-time, is a function of X1, X2, and Y. And it can be written in this form, integral dx1 dx2. There's going to be some coupling constant here, squared. Okay, so this is the 4-point function. And this turns out a nice way to think about this object is that, first of all, once you massage it in this form, it's like a Schwinger parametrization of the standard. So you'd have to do 2 time integrals here, but you can replace the time integrals over these 2 like Feynman Schwinger parameters, x1 and x2. So it's just standard time integration. But when you stare at this formula, I hope it screams at you that it looks like a loop diagram. There's some propagator, some rational thing, and then there's some measure to the power epsilon. So it looks like a gym rag type of loop integral. And then we immediately thought, oh, let's look at how amplitudes people deal with this type of integral. But before I go there, let me just make a remark that there's a nice way of thinking about this formula. That the cosmology introduces some measure, and what you're supposed to integrate this rational function inside is the wave function evaluated in flat space, meaning when there's no time evolution. But now you see that the little x's are appearing here, or is it the big axis, where you take the big axis and you shift by these little final parameters. We keep y untouched. Okay?
Is it in the regression range of this one?
0 to infinity, yeah, sorry. So you integrate in the upper quadrant. So this is a deformation that we found, and now actually there are other deformations that we thought that this is just a stupid toy model, but now there are other deformations that you should really think of this as some sort of skeleton. And then there are different ways of filling it up to get some real body. So this is one way that lends you to some cosmological wave function. Just for fun, I'm not going to discuss this, but let me just mention that there are a couple of other things you can do that bring you closer to reality. So the one thing you can do, for example, is you can take psi flat, keep the axis unchanged. You can rescale the exchange variable y and integrate again from 0 to infinity against the kernel that looks like this. What this does is it changes this propagator of a conformally coupled or massless field for the propagator of a non-particle, or in other words, the CFT operator, scalar CFT operator of dimension delta. Okay, so that's a simple deformation you can do. There's another deformation that is slightly more sophisticated. We need to introduce two of those T parameters that engineer essentially the growing, the decaying mode of a massive field in de Sitter space. So you can also get a de Sitter. So going back to Edward's question, I suspect that if one put enough bells and whistles here, you'll be able to get a nice integral representation when all the particles are massive here. And I think that the technology that we're developing to attack this diagram will be useful also when you do generic masses in the Sitter space, but this is still speculation. So, okay, so what happens? Let's go back to this example. So you can imagine trying to find differential equations for this. And there's something really beautiful about this way of writing the integral, in that the integrand is only singular in certain lines in the integration domain. So here, the integration domain is x1 and x2. And even though you're integrating over the upper quadrant, there are some lines or planes for which this integrand is singular. So there's, of course, the lines at the origin. Then a certain value of x1, a certain value of x2, and a certain value of x1 plus x2. So it carves up the integration domain into some bounded chambers and some unbounded chambers. And then there's lots of beautiful mathematics that comes into play that tells you the way forward, okay? So given that I'm very bad at time management, I'll just tell you what the answer is. So what you're supposed to do is, instead of trying to find a differential equation for this correlator, you're supposed to think of all integrals that are only singular on these lines. So you could imagine, for example, putting an extra factor of x1 downstairs, or changing the exponents of these guys. So you get a whole family of integrals, but they're only singular in these lines. So if you think of the whole family, then there's a theorem that claims and we checked zillions of examples, and there's a proof that I don't understand, but there is a proof that they form a finite dimensional vector space, meaning if you know a handful of these integrals, you know all of them. That's the first fantastic statement. It really follows from the fact that you can do partial fractions and integration by parts. That it's not that you keep generating newer and newer functions. Sometimes you generate a total derivative. Sometimes these integrals are related to each other by partial fraction identities. So that's one thing. The other thing is that there is an upper bound on the size of this vector space, which is the number of bounded chambers. So here it's 1, 2, 3, 4. So if you know 4 of these integrals, you know all of them, from which the differential equations will immediately follow. Because then if you take 4 of these integrals, let's take the original wave function, and 3 other guys, F1, F2, F3. As long as they're independent, they depend on the kinematical data, X1, X2, and Y. If you take the total differential of this, all that you're doing is you're changing the denominators, just increasing the powers. But that is just a change of basis in the same space. Okay. And that's it. That's the differential equation. So that's where the differential equations come from. This is nice, but if you choose your basis incorrectly, the equations that you end up with are a whole mess. Moreover, this is an overkill the moment you go to more sophisticated diagrams. So if you, for example, consider now this diagram here.
So here's the D's one. The D's with respect to which variable?
X1, X2, and Y.
All of them.
All of them, yeah. If you go, for example, to this diagram here, it depends on, let's say, X1, X2, X3, Y, and Y prime, function of 5 variables. There are 3 integrals to do, 3 time integrals to do, and you have a bunch of planes now. So you're gonna carve up a 3D space of a bunch of planes. There are 9 planes. In this example, there are 9. I just tell you the numbers. It's not relevant, but there are 9 planes. They actually, I never visualized this. It's hard to make it in mathematical, visualizable way, but it carves the domain in 25 bounded chambers. And so you would think that you need a 25 by 25 dimensional matrix to find the differential equation here. But then comes a little surprise that the physical example is much, much special in the space of all such integrals. So all you really need is a 16-dimensional space, okay? Meaning if you know 16 of these integrals, the system just closes on its own. You don't need to explore the entire vector space.
So are these flat connections?
Yeah, they're flat.
Regular singularities?
That's right, yeah.
No irregular singularities?
Yeah, for this toy model, it's all a bunch of d logs of certain functions of the kinematics, yeah. So for example, in this example here, where are the singular points? So I described already 2 of them for you. When you take the sum of energies going to a vertex to 0, that would be x1 plus y, x2 plus y. Then when you take the sum of all the energies to 0, which would be x1 plus x2. But it turns out that because, well, we can discuss maybe offline why, but you need 2 more. You need also x1 minus y and x. So there are 5 singularities. So in this case, the matrix A, it's a 4x4 matrix, which is a sum of 5 d-log forms. These are the 5 d-log forms, and with some coefficients.
Do you know the representation of the fundamental group?
No.
Do you know if that singularity structure really depends on having this power law FW, or would remain the same for a generic FW, for example?
No, I think it relies on the fact that it's power law, because then this is related to the fact that the scale factor is power law.
So if you have something that interpolates between different things, then the singularity structure.
If you want something like lambda CDM, sum of powers, then I'm not sure that the structure will remain. Sure. Okay, so, am I out of time? Is it true?
Maybe,
Do I have 10 more minutes?
you can have 10 more minutes.
Okay. So, then these differential equations are, okay, this is a 4x4 matrix A. This is a 16x16 matrix. And, well, you can imagine what happens. So if I add one more propagator, then I don't remember the number of planes. The number of bounded chambers is of order 200, 200 something, 202, I forget, but it's 64. Okay, so now we can interpolate. So it's 4 to the n, 4 to the number of propagators, the size of the basis. And, okay, so you still need to bookkeep a huge matrix, which people in amplitudes are happy to do. There's no problem, you can bookkeep. But then we found something very cool, that now you can forget about time integrals. I give you some rules, and you can predict all the entries of the matrix A. Okay, so this is what we call kinematic flow. So then we wrote, the rules are sort of contrived. We needed 4 rules, and yeah, you needed to suspend belief for a little bit to accept them, and then you can write all the entries of the matrix A. But now it turns out that if you go back to the formula, it did not erase.
If I think it's flat to action, I could change gauge. Are you saying there's a nice gauge?
There is a nice basis in which you can predict all the entries of the matrix A. I think it's a very interesting question. How the gauge invariant information is encoded in the.
That's why I asked about the representation of the monodrome of the fundamental group.
Right.
Codes gauge invariant information.
Yeah, but that
looks complicated.
yeah. I don't think that people studied this like these Wilson loops and so on. It's an interesting question. Now I'm going to describe a basis in which you can not touch, no integrals will be harmed. You just draw some pictures in kinematic space and you get all the entries of the matrix A. Okay, with 2 rules, only 2 rules, very simple rules. But you need to give me 10 minutes from now. Okay, so first thing is why 4 to the n? So for each propagator, this propagator has 3 terms. So you could imagine instead of sticking in the full propagator here, you're sticking 1 term at a time. And that will give you 3 basis members out of the, so for n propagators, 3 to the n. So why do you get 4 to the n? But if you remember from the differential equation here, what was the goal in life of this differential operator? Was to collapse the propagator, right? So that tells you what the 4th option should be. The 4th option should be you should always stick in a delta function. Okay, so to make things scale, you can stick in this scale invariant delta function. So these are the 4 choices. So that's to say, if you take the standard perturbative wave function, that is a product of these bulk-to-bulk propagators integrated over time. But now you, for each one of the propagators, you stick 1 at a time, one of these 4 choices, each time ordering for this disconnected piece, the piece that only ensures the boundary condition, or the delta function, you get 4 basis members and you generate the 4 to the n basis members of. And this is I claim it's a very wise choice after staring at this for 5 years. And now I tell you, forget about differential equations and forget about these integrals. So these integrals were very useful to tell us the strategy, but in hindsight, they're a huge red herring. We should have just gone and used standard time representation. So now, I'll tell you a neat way of thinking of kinematic space. And then I'm going to write the equations. So the first thing you're supposed to do is do tubings of kinematic space. So let's start with the 4-point example. 1, 2, 3, 4. So because the next channel diagram, remember that it didn't depend on K1 and K2 individually. So you can look at the dual graph and think of, instead of the quadrilateral, you can think of this dumbbell picture, where here goes x1, K1 plus K2, here goes x2, K3 plus K4, and in the middle goes y. And because of this funny story about y appearing with plus or minus sign in the propagator, then you need to allow for these two types of singularities with plus or minus. So to bookkeep that, we put a little cross here so that you know, depending on how you tube, whether you're keeping track of x1 plus y or x1 minus y, okay? So this is the tubing of, let's just, let me try to do it in parallel, the two boards. So now if we do the 5-point example, x1, x2, x3, y, and y prime. So the kinematic space looks just like this, x1, y, x2, y prime, x3. And so the first rule of these tubings is that I need to put little tubes, I guess, on top of each one of the vertices, and they should not overlap, but they can enclose the cross or not. So this gives me 4 possibilities. So one, this is one, then the 3 others, this. So this is all in kinematic space, but it's in one-on-one correspondence with the 4 choices I mentioned. So one way to think about it is that this is the disconnected piece where each time evolves on its own, is the last term of the propagator. This one is where they both evolve together, so it's the delta function. Well, these guys give some error of time, even though I'm in kinematic space. Okay, so here there will be 16 tubings, and I will show you. I'm going to use, well, Nima is the chair, so I guess let's see how much he lets me. So I'm going to try to tell you the differential equation for this guy here. This is one of 16 guys. But let me write the differential equation for this example. So these tubings have double duty in life. So they parameterize the functions. So these are related. So to a given tube, I associate one basis function. It's related to one of the 4 choices there for the propagator. But they also control the singularities that appear in the differential equation, okay? So, for example, for this guy here, now I need to do some polar management. I get epsilon. So what is the meaning of these guys here? So this is just one of the basis functions. And this is the ladder that is associated with this tubing. So this is d log of x1 plus y. And this is d log of x2 plus y. Okay? Just to keep you on track, this will be d log of x1 minus y. That's why I put the cross. Remember to keep track of the plus or minus sign. And this is d log of x1 plus x2. Okay? So there are 5 types of tube. This guy, this guy, this guy, this guy, this guy, which are the 5 ladders. So this is one differential equation. Now, for these guys, it will be symmetric, as you can imagine. But it's more interesting. So you get this. Epsilon you get one term that goes like epsilon times the same guy, times each individual tube, this tube, plus this tube, the sum of 2D log forms. And then there's a new thing.
Sorry, was epsilon the parameter describing the cosmology?
That's right, yeah. If I'm doing phi cubed. Strictly speaking, if you change the polynomial, there will be a parameter here that is related to how many legs are coming in. But I'm just for simplicity doing phi cubed, okay? Right. Now there will be a new term here, and it looks like this. We call this F because it's strictly speaking not in the wave function, it's related to the fourth choice of sticking a delta function. So this, even though it's all democratic here, these three guys are sort of size, they're just different parts of the wave function. This guy we call F because it's a bit like a source, right? When you call F a propagator. And I forgot to call it soon. And now there's no epsilon here, okay? But the important point is that you oops, I think I messed up. Yes, I messed up, sorry. Looked at the wrong line. This is just the same. So what's going on? So you either activate the tubes individually or they are allowed to merge. So why are they allowed to merge? Because sometimes when you hit with, you see in cosmology, you trade, this is maybe the most important takeaway of this talk, you trade distances in space for times, because the longer the spatial distances that you're probing, the earlier in time you're probing, because these things were redshifted more or less for an accelerating cosmology. So here, when you hit these things with energy derivatives, you're essentially hitting them with time derivatives. So sometimes you hit something with a theta function, you generate a delta function. And in kinematic space, what the way to encode this is that these tubes sometimes grow and merge, which is what's happening here. So now I declare that you can do your favorite tree-level diagram without touching any time integral by two rules. Activation and merge. So just takes the rules and I'll write I'm not gonna torture you with a 16 by 16 matrix, but I'll just show you one line and then we'll stop. So the first activation rule is you take all the tubes of a given basis function and you activate them one at a time. They're the associated D-log forms times epsilon times the original mode function, okay? So you call all tubes one at a time and it generates the denominators that appear in the differential equation. And the other rule is that they can merge. So when you activate a tube that has a cross, it's allowed to merge with the tube adjacent to it. And then you see here, you hit here there was nothing with a cross, nothing was activated. Here you activated something with a cross, so these guys are allowed to merge. And what multiplies the function related to the tube after merging? It's the difference between the original tubes. With an extra rule that the plus sign goes with the guy with the cross. So that's everything in life. It's easier to learn from example. So let's write this guy and I'll stop. This is real beautiful, beautiful. Okay, so sorry, I have to show you because it's kind of amazing to me. So you're gonna activate the three tubes one at a time. So you activate this guy. I'm not gonna call her. I hope it's clear now. So this is d log of x1 plus y, x1 minus y. This is d log of x2 plus y minus y prime. Okay, so you always take the y's that enter a vertex. Times the original side itself. But now you see these two tubes here, they have crosses, so they're allowed to merge. So now I get one term that comes from this merger here. So it connects these two tubes. So I write that's this guy minus this guy times the function that is associated with this merge. You see these two tubes now fused, and I got this new basis function. And then there's also this other merge here, which will be minus, oops, sorry. So I activate this ladder first, and then this ladder, then these two tubes merge, and I get another source function that is related to this tubing here. So I activate, so okay, so you go home, at dinner tonight, you tell yourself, you activate, well, you can draw your favorite tree, okay, just put crosses on it, and then you activate one tube at a time. When the tube has a cross, you can merge with the neighbor, and then don't forget about this relative sign, and then you can go and check that the fact that this is a connection that closes, that it's a flat connector and so on, is highly non-trivial. It relies on some three-ladder relation among these ladders and so on. It's not at all straightforward, but somehow it works. And if you go back to this simple representation, time representation, you can prove it by simple integration by parts, identities, and so on. So I hope I gave you, sorry I rushed at the end, I hope I gave you a flavor that these very simple structures, they rely only on this reheating surface, on boundary kinematics, and somehow they know about time evolution. It's in a very simple toy model, but now I'm getting more confident that there are deformations of this toy model that bring us closer to more realistic models and can give us some new insights into the structure of these initial conditions. I'll stop here.
I have a quick question. What is the just of time here?
Well, here you have differential equations that only depend on boundary momenta, and the solutions are, okay, strictly speaking, I would like to prove, which in the hyperplane arrangement story we weren't able to. There is this structure of tubings. You can write a system of differential equations that closes on its own, only depends on spatial kinematics, and the solution to the system of differential equations are time integrals. But we work it backwards. We know the time integrals and we find the system of differential equations, but we know that there's a way of getting them without ever touching them.
Does d squared equals 0 follow purely from the rules, or do you need to know about the time integrals to get d squared equals?
No, you don't need to. The only thing you need to know is that the ladders associated to adjacent tubes are related to the ladder of the merged tube. That's it. So you don't need to know.
When we had the same picture for what labels the functions and the same letters.
But the functions we were associated to each tubing were
They're
different.
different. I see. The base is the same, the size of the bases didn't change. It's
That's
still-
right.
It's still coordinate dimension.
That's
So
right.
there's some basis choice of our choice that's.
And actually-
that comes from the time.
That's right. And actually, our intuition was coming from the time representation, but we never bothered to take the actual time representation and see what that gives. And that's the new thing. And remember, we had in the paper with Nima, we had 4 rules. The rules had fine print and so on. And then in this basis, it's much simpler. I don't know how to answer the question, what's the invariant contents, right, of this this flat connection, right?
There is some fundamental group that you can, in principle, work out. It's not.
Yeah, but
It's not
how
very
that's
easy.
reflected in the differential equations, I think it's not clear.
Yeah, I think something that's a little funny is that, I mean, that's there in the entire story, is that to get the actual wave function, you need to go to this 4 to the n dimensional space. Whereas, for example, if we're in flat space, that's the answer, right? You know, we have, so in order to see that that's the answer in flat space from any of this differential equation method, it seems sort of miraculous that you
Yeah.
can pick out this one thing. I
That's
think the sort
true.
of conceptual difference between what you're doing now and what we did before is that we really began from the flat space deformed representation that's kind of closer to seeing the simplicity in flat space.
Agree.
This is starting from the time integral representation that's sort of making
Yeah.
cosmological things from there on.
Yeah, by the way, I think it's just to echo Nima's point, when epsilon equals -1, all the solutions of these differential equations are rational.
Right.
And they give back, when you add them in the proper way, they give back the.
Totally
rational-
unobvious. Yes, that's right.
And it's not obvious at all. And when epsilon is 0, it's a polylog. When epsilon is generic, some hypergeometric stuff, it's it changes wildly, right? The analytic structure as you change epsilon.
This business of differential equation versus the time is this similar to a problem that's in quantum mechanics where you determine the ground state wave function by solving the path integral or in that case we do need to know the ground state energy.
Yeah. Yeah, I think it's morally related, but I don't know how precisely related.
In flat space, it's identical.
Yeah,
It's flat.
no, but in cosmology,
But just to say, in flat space, you can either do the path integral, which is the time integral, or you can
Right.
solve Schrodinger's equation.
yes, yeah,
And the direct solution of Schrodinger's equation in old-fashioned perturbation theory is the two.
is this one, yes.
So that's, in that case, and so if you like, if you said sum over tubings, that's a wave function. Wow, it comes from a time integral. That's precisely the path integral versus the Schrodinger equation.
Right.
I agree. In cosmology, it's a slightly more interesting question.
Yeah,
We can certainly go back from these boundary things. We can sort of produce from them by doing another transform. We can produce the time evolving wave function
mhm,
and produce out of this object by yet another kernel something that solves the bulk Schrodinger equation. So
Right.
and so maybe that's the path to sort of connect these two.
yeah. Yeah, it'll be interesting to see how these sources appear, for example, as you try, it's not obvious how they appear when trying to solve the Schrodinger equation. These guys appear naturally. But not this, for example, these are all rational with simple poles in flat space, but these have double poles, for example. It's 1 over total energy squared, and higher poles depending on how many of these vertices you tube. So these I don't quite understand how they are appearing in the Schrodinger equation.
So from the time integral picture, right, like usually you get functions that have spurious poles. Right, like, I mean, that when you then simplify the tubing picture, they all cancel out. So do your differential equations?
Yeah, they all have
They all have spurious
they'll have
poles.
spurious poles, and then, so these guys will have spurious poles when you have.
Yes.
Actually, no,
Is there dual
is
log?
that true? No, I thought.
The final dual log, correct?
Yeah.
No, I think in this case they don't. I think that in this case they'll, I think you can, sorry, no, I take it back. No, each case will not have spurious poles. You can impose boundary conditions to remove the spurious poles, and then they will give an answer. For example, this guy here will give 1 over x1 plus y times x1 plus x2. It's not gonna have the 3 poles. It's gonna have just part of the answer. Then when you put everything together, then you have. the usual.
Sorry, in flat space, they all definitely have spurious
Yeah.
poles.
No, but you can solve the differential equation in such a way that each of these guys individually don't have the spurious poles.
But that's by boundary conditions?
No, so maybe in the old basis.
That's what I'm asking. This
No,
is-
yeah, maybe
that's-
there-
I think this is probably the
Yeah, this
key
is the
difference.
point.
Yeah,
Yeah,
yes,
that's
yes,
what I
key
was
difference.
trying
But no, in the,
Yeah, that's, I think, the invariant content of the.
yeah, there are 2 stores. So there's the old basis, which we have contrived rules, and there you can find solutions that don't have these spurious poles.
Yes.
Now, in this basis, there are spurious poles, but the rules are much simpler.
Yeah, that's okay.
By the way,
That, by the way, is even true for the flat space wave function, because the number of terms that you get when you just compute the flat space wave function is, like you said, 3 to the e.
Right.
Whereas the number of terms in old-fashioned perturbation theory goes like e factorial.
Right.
However, the big advantage is that all those e factorial terms are physical poles, and all of these things are massively spurious. Okay, now there's more justice in the world, so.
Yeah, but, okay. Or maybe this is getting too, but there's a cool story about the boundary conditions also, that for each sector, this absence of folded singularities of the answer fixes all the boundary conditions up to one term. And then factorization of the final answer ties all these terms one with each other. So this I have to show you offline because it's kind of a cool piece. So in the old story, the boundary conditions, you couldn't really go to the physical singularities to fix the solution. Here you can go to the physical singularities to fix the solution. And then everything gets tied together by factorization and absence of these spurious singularities. You should probably go get cookies.
Yes, I got this thing.